Hello everyone, and welcome back to this NPTEL lecture series on cycloaddition reactions. So in the last 3 weeks we discussed a lot about 4+2 cycloaddition and 3+2 cycloaddition reactions. So the next 4 lectures what we will do, we will focus mainly on 2+2 cycloaddition reaction. So when we talk about 2+2 cycloaddition reaction, so this 2+2 cycloaddition reaction is of 2 types. One, this can be done under thermal condition, so which we call it as thermal 2+2 cycloaddition. The other one is also, the other one can be done under photochemical condition, so it's called photochemical 2+2 cycloaddition reaction. So under thermal condition, not all alkenes can undergo 2+2 cycloaddition. Only select alkenes can undergo this thermal 2+2 cycloaddition, like allenes, ketenes, vinyl cations and isocyanides. So these are commonly used 2-pi components in thermal 2+2 cycloaddition reactions. When in photochemical condition, one can use 2 alkenes which can undergo 2+2 cycloaddition reaction, and you also can take 1 alkene and 1 alkyne to get cyclobutene, and the third option is one of them is an alkene component, the other one is a carbonyl component. Now let us straight go to thermal 2+2 cycloaddition reaction. As we have discussed in 4+2 and 3+2, in both cases it is quite obvious that thermal 4+2 and thermal 3+2 are allowed, because both involves 4-pi electrons plus 2-pi electrons. However, in the case of 2+2 cycloaddition, we know that the 2-pi component is reacting with another 2-pi component. So if you take HOMO of 1 alkene, because there are 2 alkenes which are involved, so the HOMO of the first alkene is this one, then obviously you have to take the LUMO of the second alkene. So now if you take this LUMO of this second alkene, what you see is the bonding happens at only one end. You can see the bonding happens at one end, whereas the other end you see an antibonding. So obviously this should not lead to a formal 2+2 cycloaddition reaction. However, if you take this LUMO of the second alkene and rotate it by 90 degrees, that is, you just rotate towards you, then you will get, or you will see the orbital from the top, like this. Now again you rotate it by 90 degree anti-clockwise, you rotate it by 90 degree, so you get this. So this is the LUMO of alkene 2, and you have the HOMO of alkene 1 here. If you bring these two, what will happen? You will get this particular arrangement. Now you look at this arrangement, you can see bonding is possible here and bonding is possible here. Or in other words, if the HOMO of one alkene and the LUMO of the other alkene, if they approach each other perpendicularly, then thermal 2+2 cycloaddition is possible. So now if you see, this is 2 pi s, that is, this one is 2 pi s, that is supra, the other one is antra. So this is 2 pi s and 2 pi antra interaction is possible provided one alkene approaches the other alkene perpendicularly to form this cyclobutane. So that means 2 alkenes should approach like this. One alkene should be like this, other alkene should come perpendicularly. So then only this thermal 2+2 cycloaddition is possible. And as we know, thermal 2+2 cycloaddition is symmetry forbidden under supra-supra condition. However, as we have seen, This is possible under supra-Andra condition. So this is what just we discussed, and if you have a closer look at, you can see this also can be written or drawn like this. When you look at this closely, okay, what you see is there is always a steady crowding in such a transient state. That is because these two are like this, okay, and if you put any additional substituents, and that will make it again this reaction difficult. Further, the orbital overlap, you can see here, this orbital overlap is not that high. So that is why thermal 2+2 cycloaddition is not as facile as photochemical 2+2 cycloaddition reaction. So normal alkenes won't undergo thermal 2+2 cycloaddition. Only alkenes like ketenes, allenes, isocyanates and vinyl cations are known to undergo thermal 2+2 cycloaddition reactions. So, and if you look at all these four components, all these four alkenes, the central carbon atom is sp hybridized. Okay, so that is very important for thermal 2+2 cycloaddition reaction to happen. First, let us start with ketene. So how do you prepare ketene? Okay, so ketene, as you know, is commercially available as diketene. Okay, because ketene undergoes dimerization spontaneously. So if you want ketene, you have to heat it. So that means it will undergo retro 2+2 to give your ketene, and that ketene should be used in situ. Another method, I am sure all of you would have studied, on ester synthesis, where if you want to homologate a carboxylic acid, what you do is convert carboxylic acid into acid chloride and then treat with diazomethane to get alpha diazoketone, and this upon heating or under photochemical condition it rearranges to give this ketene, and now addition of water will lead to carboxylic acid with one carbon more. So this is the second way to generate ketene. And third method is if you have an acid chloride and then if you treat with mild bases like triethylamine, this can undergo elimination of HCl to generate ketene. One can do that easily if we have two chlorine atoms attached. That means that hydrogen is more acidic. So if you treat with triethylamine, it is easy to form dichloroketene, which is also more stable than this dimethyl ketene. Another method is if you have alpha chloroacetyl chloride, then you can use metals like zinc. So that will facilitate the elimination of zinc chloride to give the ketene. One can also do that with trichloroacetyl chloride. That will also give corresponding dichloroketene on treatment with zinc. So these are the ketenes one can easily use in thermal 2+2 cycloaddition reaction. In all these cases, these ketenes are in situ generated and reacted with the other alkene. So for example, this dichloroketene, which can be generated by two different methods. Now upon treatment with the cyclooctane, okay, this upon treatment with cyclooctane, so they got a product which is a bicyclic compound, and this is a Z alkene, and in this bicyclic compound what they have seen is it's a cis fused ring system. Likewise, when they took the E isomer, what they got was the trans bicyclic ring junction. So what does it infer? This confirms that the alkene approaches the ketene in suprafacial manner. So when it is Z alkene, you get cis ring junction. When it is E alkene, you get trans ring junction. How about regiochemistry? For example, if you take this diphenyl ketene and then treat with an alkyne having an electron donating group, so what you get is this cyclobutene, where this methoxy and then carbonyl are opposite to each other. The same thing now if you take instead of triple bond, double bond, okay, dimethyl ketene and simple enol ether, at room temperature it can easily undergo a 2+2 cycloaddition reaction, and there you will find only this isomer and not the other one. So, why only you get this isomer? So, if you look at the HOMO and LUMO of your two alkenes, in the case of ketene, this particular carbon is more electrophilic because it has the large LUMO coefficient. Likewise, if you look at this enol ether, then you see that particular carbon is more nucleophilic because it has large HOMO coefficient. Because of this, you get exclusively one regioisomer, and the bond will first form between these two carbons. And this is nicely exploited in sugar chemistry. For example, glycols like this, if you treat with any ketene, for example dichloroketene, and that will give this intermediate, and this intermediate has been successfully converted into a very useful C1 methyl compound in few steps. And these ketenes can undergo spontaneous dimerization. As I said, when you talk about normal ketene, the ketene itself is obtained from diketene by heating. That is, it undergoes retro 2+2 to give ketene. If you keep the ketene as such, what will happen? It will undergo spontaneous dimerization to give the diketene. And if you take like this exocyclic ketene, that also can undergo a spontaneous dimerization to give 1,4-diketone. And sometimes this ketene can undergo 2+2 cycloaddition with a carbonyl group. For example, if you take benzoquinone or substituted benzoquinone, then you will see this carbonyl oxygen has the highest HOMO coefficient. That means if you take benzoquinone or substituted benzoquinone, this upon treatment with any ketene, that will undergo 2+2 reaction between the ketene double bond and the carbonyl oxygen to give this 4-membered lactone. So, this is about regiochemistry, but how about stereochemistry? See, for example, you take a ketene with the substituent here is ethoxy group and simple alkene. So, we know now it should give 1,2 disubstituted compound. But what about the stereochemistry at these two carbon atoms? What you get is interestingly the cis isomer. Normally, if you look at the 2-dimensional version, you may think that this ethoxy and an alkyl group should be trans to each other, but what we get is cis. Why? This particular compound is a kinetic product and the trans one is thermodynamic product, but this reaction gives the less stable kinetic product because you have to look at the transition state. So, if you take this ketene and bring your alkene in such a way that the R group and ethoxy group are far away from each other. You can see R group is here, ethoxy is there, both are far away. Now, if these two undergoes 2+2 cycloaddition in this transition state, what you get is this compound. Now, you can see this hydrogen and this hydrogen, they are cis to each other. That means you will see this R and ethoxy. If you rotate the cyclobutane properly, you will get this product where ethoxy and R group are cis to each other. Okay. What happens? Now you have taken simple alkene where R is an electron donating group. Now if you take a diene where you have a methoxy group at terminal carbon, and obviously this particular carbon has the highest HOMO coefficient. Okay. So, will it undergo 4+2 or will it undergo 2+2? At low temperature it undergoes 2+2, that is between these two you get this cyclobutanone ring. Okay, this is a 2 plus 2 adduct at 0 degrees. Now, when you increase the temperature and bring it to room temperature, this looks like it's a direct 4 plus 2 cycloaddition product between 1-methoxybutadiene and diphenyl ketene, but it is not so. It is obtained from the 2 plus 2 to 4 plus 2 via a 3,3 sigma-tropic rearrangement. If you want to write, you can see this is carbon number 1, this is carbon number 2, this is carbon number 3, and again you can see this is 1, 2, 3. Now, if you do 3,3 sigma-tropic rearrangement, what you get is 4 plus 2 adduct. So, this does not come directly as a 4 plus 2 cycloadduct. It comes via 2 plus 2 cycloadduct followed by 3,3 sigma-tropic rearrangement. So, now you have diene and ketene. Will it undergo Diels-Alder or thermal? 2 plus 2. For example, you take cyclopentadiene and then treat with dichloroketene. Dichloroketene, we all know it will undergo 2 plus 2. So, then with cyclopentadiene, one of the double bonds will undergo 2 plus 2 cycloaddition and not both double bonds to give 4 plus 2 cycloaddition product. So, what you get is only this. Now, these two chlorines can be easily removed by treatment with zinc and acetic acid. Now, if you treat with excess zinc and acetic acid, what you get is this compound. Many times people misunderstand that there is a carbonyl group, okay, there is a carbonyl group attached in the ketene. There is a carbonyl group part of the ketene, but that has no direct effect with alkene. It cannot act as an electron withdrawing group, okay, because this is orthogonal, this is double bond and this carbonyl is like this. So, there is no overlap. So, having a carbonyl group as part of ketene is of no use for ketene to behave like a proper dienophile in 4 plus 2 cycloaddition reaction. So, that is why it reacts as a 2 pi component and it undergoes 2 plus 2 cycloaddition reaction. So, now this 4-membered ring, that is cyclobutanone, upon treatment with MCPBA can undergo a Baeyer-Williger oxidation to give this bicyclic lactone. So, here is another example where a ketene can undergo a 4 plus 2. The earlier example, it underwent 2 plus 2. Now, you can see that was with dichloroketene, here it is with diphenyl ketene. It also depends on the nature of the substituents attached to the ketene alkene. Okay. So, here what happens, the carbonyl group of the ketene at very low temperature, okay, minus 20, it undergoes a 4 plus 2 Diels-Alder reaction. We can call it as hetero-Diels-Alder reaction. Okay. Now, again, as I have written here, you can see 1, 2, 3 on the left, 1, 2, 3 on the right. This can undergo at room temperature or even at 0 degrees a 3,3 sigma-tropic rearrangement. Here it is Claisen rearrangement to give 2 plus 2. In the earlier example, what we saw was first it underwent a 2 plus 2 cycloaddition followed by a 3,3 sigma-tropic rearrangement which gave a 4 plus 2 cycloadduct like molecule. Here first a 4 plus 2 hetero-Diels-Alder reaction takes place followed by 3,3 sigma-tropic rearrangement to give the finally a 2 plus 2 cycloaddition product. Okay. And if you take cyclopentadiene and a ketene having only one alkyl group, okay, so this simply reacts 2 plus 2, and in this particular case you will see the ethyl group is endo with respect to diene when it approaches. So, you can see the ethyl group and the alkene are in the same side. Okay. So, only here when you have the phenyl group electron donating group attached to the ketene, the carbonyl group undergoes 4+2. Otherwise, always you will see ketenes undergoing 2+2 cycloaddition reaction. So far what we discussed all are intermolecular ketene cycloaddition. Is it possible to have intramolecular ketene cycloaddition? So that means you have to have an alkene and also ketene precursor in the same substrate. So in situ ketene should be formed and that ketene should undergo 2+2 cycloaddition with an alkene present in the same system. So for example, if you see here, you have an acid chloride and a double bond. Okay. Now if you treat with base, so what will happen? So the base will pick up this hydrogen and eliminates the HCl to generate this compound. So the methyl group here becomes this exocyclic double bond and this undergoes an intramolecular 2+2 cycloaddition reaction. And the regiochemistry again, if you look at the alkene, this particular carbon has a large HOMO coefficient, and we know this is the one which has large LUMO coefficient. So the first bond will be formed between these two and then followed by these two to give your bicyclic system where you have 5-membered and 4-membered rings fused together. But if you have, instead of terminal alkene, if you have an internal alkene where the alkene is a tri-substituted one, whereas the right hand side portion is same. Now if you treat with triethylamine, what you get is same ketene, but the coefficient of the alkene carbon, this carbon has large HOMO coefficient than this carbon. So you can see the difference because of the electron donating nature of two methyl groups. The large HOMO coefficient of the carbon changes. So now the bond will be formed between this carbon and this carbon followed by this carbon and this carbon. So that means you will get a very interesting bicyclic system, but this is not fused, this is bridged system. Okay. You get a bridged bicyclic system, whereas in the earlier case you get fused bicyclic system. So depending on the nature of the alkene which you use as one of the 2-pi components, in intramolecular 2+2 cycloaddition reaction, either you get a fused bicyclic compound or bridged bicyclic compound. So here you can see this is the ketene and then you have cyclohexene which is appended to that. So that undergoes intramolecular 2+2 to give a tricyclic compound. Now see, you have a substrate which can undergo intramolecular ketene cycloaddition as well as intermolecular ketene cycloaddition. See, for example, you take this substrate and then treat with triethylamine. So it goes through this transition state and gives this bicyclic compound. Now if you do the same reaction in the presence of triethylamine and another alkene, for example, if you take this 3,4-dihydro-2H-pyran, this 3,4-dihydro-2H-pyran is more reactive. So what will happen between this alkene and this alkene, this is more reactive. So you will see that the intermolecular 2+2 cycloaddition between the ketene which is in situ generated and this glycol or 3,4-dihydro-2H-pyran is more facile than the intramolecular 2+2 cycloaddition. So like ketene, yes, allenes also can undergo 2+2 cycloaddition. So for example, if you take this chloroallene, so if you leave it for 4 days, so it can give very interesting this cyclobutane with 2 exocyclic double bonds, and there is a possibility that it can give either head to head or head to tail. Okay. The 2+2 cycloaddition can be either head to head or head to tail if it is symmetrical allene. Okay. And if it is not symmetrical, okay, then the chances are that you can get 4 different isomers. Okay, this is again symmetrical, but if it is unsymmetrical, okay, so you can see this is unsymmetrical, so it can give one head to head, then head to tail, then tail to tail, then you have also have tail to head. So these are 4 different possibilities when you have only unsymmetrical alleles. So one can also do this reaction with siloxydienes. As you know, when you have electron donating methoxy or siloxy group, so this can react with allenes. For example, if this reacts with allene carboxylate, okay, so this or this can undergo 2+2 cycloaddition. So because of steric reason, this will undergo 2+2 to give this cyclobutane, and now if you remove the TMS group with paratoluene sulfonic acid, so you get the hydroxyl group. This can undergo anionic oxycope rearrangement. Okay, so this is not Claisen, it is anionic oxycope rearrangement. So that will give you these 2 products, which we can call it as exo or endo. Okay, so this is the major product. Okay, try to write mechanism for this particular anionic oxycope rearrangement. We know now we have discussed the use of ketenes and allenes in 2+2 cycloaddition. As I said in the second slide, isocyanates and vinyl cations also can be used in 2+2 cycloaddition. So for example, like this isocyanates can readily undergo 2+2 cycloaddition with any alkene. For example, if you take cyclopentadiene, so one of the alkenes can undergo 2+2 with this isocyanate followed by removal of this SO2Cl gives this bicyclic lactam. Instead of allene, suppose if you generate a vinyl cation, so this particular reaction is called Smirnov-Zamkow reaction. So if you take this alkyne and then add chlorine, so one molecule the chlorine adds and it generates this vinyl cation that immediately undergoes 2+2 cycloaddition to form this cyclobutynyl cation. Then the Cl minus attacks, you get highly substituted cyclobutene. And this also can be generated like this vinyl cation by adding HCl to allenes. So when you do that, first it forms this methyl vinyl carbocation, and that adds in a 2+2 fashion with allene to generate this cyclobutane and a carbocation. Now the Cl minus can attack to give the dichlorodimethyl cyclobutane. Okay, so these isocyanates and vinyl ketones, they can be easily used to make substituted cyclobutanes and butenes. And the last 3 decades, I am sure all of you would have studied metathesis reaction. So the metathesis reaction involves many 2+2 retro 2+2 cycloaddition reaction, particularly involving metal alkylates. Okay, so instead of normal 2+2 cycloaddition between 2 alkenes, when it involves a metal, then this pi 2s and then pi 2s addition is allowed. So that is because of the vacant d orbital which is present in the metal. So and that leads to such nice overlap in the same phase. So if you take an alkene and then treat with this type of metal carbene, this undergoes a 2+2 to form this metallocyclobutane, and this metallocyclobutane undergoes a series of retro 2+2 and then 2+2 and leads to this exchange of this alkene. For example, if you take an alkene and then treat with various catalyst, Krebs catalyst, Krebs 1, Krebs 2, Krebs 3, Oveda. There are many catalysts which are known in the literature, and then now if you treat with this carbene, it forms this metallocyclobutane through 2+2 cycloaddition, and then followed by retro 2+2 where this ethylene is eliminated, it generates another metal carbene. Then this undergoes another 2+2 to form this metallocyclobutane, and again it undergoes a retro 2+2. Now in the process you see these two carbons underwent elimination as ethylene, and these two carbons form a double bond. Okay, basically it exchanged. Okay. So this has been successfully used in ring closing metathesis. For example, if you take this 1,5-diene, it forms the cyclopentene and ethylene, and if you take this type of bicyclic compound, it can undergo ring opening cross metathesis if you use another alkene component. So you can see this is the cross metathesis product, and also it opens the ring, and then you get vinyl group on the other side. And if you don't use any external alkene, then use the same metal catalyst, you get a polymer. So the whole process is called ring opening metathesis polymerization, ROMP. Okay. So I will stop here, and then we will continue our discussion on 2+2 cycloaddition. So far we talked about thermal 2+2 cycloaddition. In the next lecture we will talk about photochemical 2+2 cycloaddition reaction. Thank you.